We're now at the top of page 9 in our note pack. We're going to now consider a second order. A second order brings us to this particular section on our equation guide. If A is going to be in a differential rate law, we would recognize that as rate is equal to K, where K is our rate constant. The reactant A now raised to the power of 2. If I integrate that, we turn it into a straight line formula. Differentiation and integration are opposite. It's finding a straight line curve in a y equal mx plus b format. We end up with the following formula. Again, the calculus not important, but seeing how now the concentration of our reactant can be calculated after any period of time has gone by. This time we end up with reciprocals. The original concentration set under 1, the concentration remaining after a certain amount of time set under a 1, and notice now the slope has become positive. Positive slope indicates a second order reaction. We still end up with a y equal mx plus b formula, where y, the y-axis, is 1 over the concentration of A. Time is the x-axis. The m is the slope of our line represented by K. And again, the interception, the b, the y-intercept, would be the original value of A reciprocal. So let's take a look at how that develops. Our differential rate law we just explored shows rate is equal to K times the original concentration here. Second order shows that that exponent is a 2. When we integrate that rate law, we show 1 over the concentration of A after a certain amount of time has gone by. This shows me how much concentration of A is left after time went by. Set equal to K, the rate constant, and T is that time that went by in our formula, plus 1 over the concentration of the original amount, times 0. We get our formula, y equals mx plus b, where y, 1 over A, and this is after a certain amount of time. K is the slope, T is the x-axis, and the y-interslope is the original concentration of A set under a 1. Here's the big clue. If we plot a series of data and we get a straight line where 1 over the concentration of A versus time shows a positive graph, we know it's second order. However, just to keep in mind, if we get a slope that's negative, where the natural log of A over time shows a better straight line, that's how we can determine a first order reaction. We'll be entering lists into our calculator to see which one gives us the straight line. If it's a negative slope, first order, positive slope, second order. Checking out that correlation coefficient on your calculator screen, the R constant, seeing which one gives us a closer number 1. So, important, one way to distinguish between first order and second order is to graph both, graphing a natural log of A versus time, or graphing a reciprocal of A versus time and comparing them. We just said if first order shows natural log of concentration versus time is linear, or a second order reaction would show the reciprocal of A versus time, gives us a better straight line. Let's begin a little calculator skill in the following lists. We'll need our graphing calculator out. Let's turn it on. Hit the stat key to go to your lists. I need to clear mine, so I need to clear list 1, list 2. And now they are. Let's enter into list 1 the time values. We'll hit 0, enter, 50, enter, 100, enter, 200, enter, and 300, enter. I'll bring the cursor over to list 2 and plot the following. 0.01, enter. 0.00787, enter. 0.00649, enter. 0.00481, 0.00380. I now have list 1, list 2 entered into my calculator. I'm going to use the calculator to generate a list 3, which I'm going to use to represent the natural log of the concentration. I'm going to make the calculator do the work for me. So what I'm going to do is to place my screen, my cursor, on list 3, up on the very top where it says list 3 up here. Now it's ready for me to hit the formula. So now that it's highlighted, I'm going to hit natural log button, and notice on the bottom it's giving me ln with a parenthesis, and I want it to find the natural log of those concentrations. So I'm going to hit natural log of list 2 equals. And now in list 3, we see a generated set of numbers that automatically calculated those natural logs. It reads negative 4.605, negative 4.845, negative 5.037, negative 5.337, negative 5.573. We also need to consider list 4. In list 4, what I want in there, I want the reciprocal of list 2. So I want the concentration of our reactant, NO2 or A. It looks like I have flipped. That's really NO2. But let's make the calculator do that for us. So again, I'm going to move my cursor to the top of list 4. That allows me to type in a little calculation. That calculation will show that I want the reciprocal, so 1 divided by, and my concentrations are still in list 2, so I hit list 2. 1 over list 2 generates the concentration of that reactant in a reciprocal. It reads 100, 127, 154, 208, 263. We need to find the best straight line, a y equal mx plus b. Is it what we're looking for? If the x-axis in list 1 is time, list 3 is the natural log of our concentration, and then again we want list 1 time, list 4 is our reciprocal of our concentration. We need to plot those in a graph and find the best straight line. So stat, calc, a linear regression, which is number 4 choice. It's asking me which list would you like. Well, list 1, comma, list 3 is going to show me the ratio between the natural log and time. And this is what my calculator says. I get an A value, a B value, R squared, and R. I want to know the correlation coefficient. So under here, I'm going to jot down R squared is 0.9824. Friends, you could take the time to visually plot this